Okay, so we did the solution for the special case in which the right-hand side was 0. So that's the homogeneous equation, and we found is that if a function and its derivative satisfy this equation, then the function must be in this form where y0, the coefficient, is the value of the function at time equals 0. So normally the equations that we will have are not in this form with the right-hand side equals 0. The equations that we will have are going to be in this form in which the right-hand side is also a constant. So if we are given a function like an equation like this, how do you solve it? It's a very quick shortcut to solve it. So the easiest way to solve it, given the work that we have done, is to say, well, you know what? Let me introduce a new function. So now I'm introducing a new function, z of time. So z of time is equal to y of time minus k. What is this function? I just made it up. I made up the function z of t. So my function that I made up, z of t, is equal to the function y of t minus k. So if I do z dot of t, so if I take the time derivative of this function, z dot of t, the time derivative of y is y dot, and the derivative of a constant is 0. So z dot of t is equal to y dot. Why do I do this? I do this because now I look at this equation over here. And I say, you know what? I can rewrite this equation as tau y dot plus y, and I bring k on the other side, y minus k, is equal to 0. And so now if I look at this and I look at that, I say, OK, so y dot is the same as z dot, so I can write this as tau z dot plus y minus k is z. T z dot plus z equal to 0. So if the y function, y of t, must satisfy this equation, my z function, which is this function here, must satisfy this equation. And so this now, again, is a homogeneous equation like that. So for this equation like this, I already know the solution. So I know that the function z of time is going to have a function like that. So my z of time is going to be equal to, so from this, I find that my z of time is going to be equal to the value of the function at time equals 0. So z of 0 equal to z0. What is the value of the function at time equals 0? Is equal to the value of the function y at time equals 0, which is y0 minus k. Right? So if I know the value of function y at time equals 0 equal to y0, then the value of the function z at time equals 0 is z0, y0 minus k. So my z of t, the same way as I solve this equation here, and I say y of t is y0 e to the minus t over tau, z must satisfy the same equation. So z of t must be z0 e to the minus t over tau. That's the solution to this differential equation. And now say, but wait a second. My z of t is y of t minus k. So I can write from here that y of t minus k is equal to z0, y0 minus k is z0, y0 minus k that multiplies e to the minus t over tau. Well, guess what? This is the equation for y of t. But before I write the equation for y of t, I want you to notice something. What happens to z, or y of t minus k, as time goes to infinity? We know what happened to this function here, where time goes to infinity. It goes to 0. You can see here that as time goes to infinity, e to the minus infinity over tau goes to 0. So this term here goes to 0. So for time that goes to infinity, what we have is we have the y of t goes to k. So k, we find by solving the equation, is going to be the value of the function where time goes to infinity. So what does that mean? We already knew k. This is the equation that we were given. So what do we do normally? If we're given a differential equation in this form, what that means is that the constant right-hand side is not just any value. The constant right-hand side will happen to become the value of the function when time goes to infinity. So the canonical way to write this equation normally is to write it as tau y dot plus y equal to y infinity. Because we already know, we did the work, we already know that this is going to end up being the value of the function at infinity. So we write it as tau y dot plus y equal y infinity because the way we normally write this equation here is y of t minus y infinity is equal to y0 minus y infinity e to the minus t over tau. So the solution to this equation here, t y dot plus y equal y infinity, if I bring y infinity on the other side, is going to be that y of t is going to be equal to y infinity plus y0 minus y infinity e to the minus t over tau. This is it. This is the solution once and for all. You don't need to derive a solution. This is the solution to this differential equation with initial conditions. The y of t is equal to y0. Oops, sorry. That's not the initial condition. That's the solution to the homogeneous equation. These are the initial conditions. Y of t equal to y0. So if I'm given these differential equations and I'm given the condition, the initial condition, that y of t equal to y0, then my solution is this. What does that equation look like? It's going to look very similar to this. In the homogeneous equation, the right-hand side is 0. So y goes to 0 as time goes to infinity. In this equation here, the right-hand side is y infinity. So y is going to go to y infinity as time goes to 0. So if I want to do the plot for the inhomogeneous equation, say that this is y0 and this is y infinity. Can be on the same side, can be on different side. It doesn't matter. So this is y0 and this is y infinity. The function will go to y infinity as time goes to 0. If y0 is bigger than y infinity, it's going to go down to y infinity. If y infinity is bigger than y0, is going to go to y infinity going up for whatever value of, so whatever is the value of the function to start with, you start off at y0 and you go to y infinity. So you can see that at time equals 0, this is 1. So you have y infinity plus y0 minus y infinity. You start at y0. And as time goes to infinity, this whole thing drops and you end up at y infinity. And it goes to the value with a characteristic time tau, which is the time that it takes for the distance between y0 and y infinity to go down by a factor. So this distance here is y infinity minus y0 over e. So it takes a characteristic time tau for the function to get closer to the final value by a function, for a function of 1 over, by a factor of 1 over e. And that's what this equation means. So this equation, this is what the equation means. So in general, you can end up having, you can solve your problems and end up, say, with an equation that looks like, I don't know, a plus c over d y dot plus y equal to f plus g over 3. This is your, after you've done all the calculation, you end up with a differential equation that looks like that. What that means is that this guy here, so he's written in canonical form because you see the coefficient of the y of the function is 1. So once you write it with a right-hand side, the coefficient to y dot, and then the function with a coefficient of 1, this is the canonical form. So once you have written like that, you can say, okay, so my right-hand side is y infinity the coefficient of y dot is tau. So if you call this y infinity and this is tau, you have written it in the canonical form. This is the solution, and then instead of being y infinity plus y0 minus y infinity, your y infinity would be this block over here, your y0 would be this block over here, and that would be your solution of your equation. So the solution to this equation here, if I have to write it, well, first of all, I need to know what is y0. Without y0, I cannot write it. But if I have y0, then I can say that y of t is going to be equal to y infinity, so it's going to be f plus g over 3 plus y0 minus f plus g over 3. And this whole thing multiplies e to the minus t over a plus c over d. So this looks ugly, but you understand what I'm saying. That is, once you're given an equation with constant coefficient, you write in the canonical form. Once you've written in the canonical form, this is your solution. You don't need to rewrite the solution. The solution is done for you. So that's about it. That's all what I wanted to say, and that's all what actually you need to solve problems for viscoelastic material. So I'm going to give you a couple of example problems so that you can practice doing this, but it's very simple, and that's it. If you want to know more about differential equations, actually, if you want to know anything, because this is nothing about differential equations, take 1803X. All right.